Hi everyone, I am Saniya and this is sleepy little Yangshi here. And in this video, I want to talk to you about equal width binning versus equal density binning, just an overview and a comparison of those. So we're going to just talk about just the main concepts in those. And what you're going to see is that I actually have prepared two videos on these topics on equal density binning and equal width binning. So yeah, I have these two videos on equal width binning and equal density binning. So one video each, where I go into depth about sort of like discrete versus continuous values, what is binning, a little bit of the biology background, and I'm motivating it in the context of binning gene expression data for patients. Patient samples, but it's just an application of equal width binning and equal density binning in a step-by-step case so that you can understand how we apply them. But in this video, I just want to just generally go over what those are, like just what is equal width binning, what is equal density binning, what are the key concepts about those binning and what they try to do. And please subscribe to my channel for more updates and please let me know if you have any questions at all. And there are two main methods that we're going to discuss, and I'm going to cover one in each video. So one is equal width binning. But for equal width binning, each of these bins has the same width, like it's 10 here, 10 here, 10 here, 10 here, 10, 10, 10. This is how like a histogram typically works, you know. So this is 10, 10, 10. This width is the same. Like just almost like a histogram. But for equal depth binning, what you will observe here is that they may not have the same, and going across the y-axis is the number of items inside those bins. So again, this is also the number of items. So what you will observe is that for equal width binning, they may not always have the same number. So this 10, just to remind you, this 10 is basically the interval. That's 10. That's 10. You know, that's the interval. For equal width binning, they all have 10 here for the intervals for this example. And, you know, this is the number of items, the number of values here. That's what this height represents. But for equal depth binning, what we observe here is that all we really care about is having the same number of items inside each bin. It doesn't matter if this one is 22 long, or this one is like 9 long, or this one is 6, or this one is also 6, this one is 4, 7, 7, 8, 18. It doesn't matter. All that. So again, just to clarify, this is this is 22, and this thing here is 9, and then this thing here is 6, and this thing here is also 6, this thing here is 18, and this is 7. So it doesn't matter like what the width is here. What they care about in equal depth binning is each bin has the same number of elements. So the difference is each bin has same width. And here, each bin should have like roughly the same width. So it really depends if it's something odd or something. Each bin has same number of items. That's what the thing is, that for equal depth binning, what we're concerned about is that each bin has the same number of items. We don't care about the width of the interval. It could be 22 or 9 or 6 or 6 or 7, for instance, or 18. It could be really long, really wide, really chunky, or it can be small. We just want the same number. We just want bins with the same number of items inside them. But like that's the same number. We're really caring about this height. This is what matters. So what we're caring about here is ultimately what we're caring about is this. We're caring about, let me show this. We're caring about the height.
We want the height to be the same. That's what we care about here. So they should all be the same height. That's what we care about. But for the equal width binning, what we care about is this. We care about the width being the same width. That's what we're caring about, this width. This width. That's the difference. So again, equal width binning cares that each bin has the same width. And again, if it's an odd issue, they should roughly be the same width. And equal depth binning cares that each bin has the same number of items inside it instead. So I'm going to kind of explain more about each of these. And then we can kind of compare them, like this is Python code kind of using this age. If you have that age variable, this sort of shows you how equal frequency binning works and how equal width binning works. So it's sort of the opposite idea that equal width binning, you may not always have the same density in each bin, but each bin is going to have the same width along. It's just like the same marks. You might not have the same, like it's the same way of binning information, like kind of putting continuous data into groups or categories, for work. So equal width, they just have the same width, but we may not have the same number of items inside each bin. But equal frequency, on the other hand, is saying that each bin has the same number of items. I mean, it's really trying to, if it can be divisible properly, it is supposed to typically have the same exact number of items inside it, but the widths of these intervals might not always be the same. As long as each one has, you just sequentially put each one in the bin, the next one in a bin, the next one in a bin, the next one in a bin, so that you have the same number of items. And this one is just like, okay, we have the bin max, we have the regions, we're just going to assign whatever comes in this region, like there. It just, everything has equal width. And this is Python code as well. Like if you want to kind of look at the comparisons of, these are two of the main binning strategies we're going to talk about today. And another way to sort of compare equal frequency or equal density binning and equal width binning is the following. So like bucketing, the concept that we're talking about, and I have another video about equal density binning, it's just like a data pre-processing step. And you're basically discretizing data. So you're dividing the data into small intervals like bins. So it's continuous data that's going across like this. And you're basically dividing this data into these bins. You're trying to divide them up into these bins. You're trying to discretize it. And then they are replaced by general value that's calculated for that bin, maybe a bin average, maybe a bin interval itself, maybe the bin number. This smooths the input data, may also prevent overfitting. If you have continuous data, maybe put the data into groups, make it less specific, make it more generalizable. So equal frequency binning, which is also called equal density binning, that I have another video on. Bins have equal frequency, so equal number of items in each bin. And equal width binning, I think of it's like a ruler as well. It's like placing these buckets out, and rainwater could fall into these as well. Like placing, buckets of equal size. They're not quite the same, but it's like placing them out and making sure that equal items fall inside it. That's what equal frequency is. Equal density, that's what it's called. So if we have the same list here, how would you divide it into 3 bins so that each bin has roughly the same number, 4 items in each bin here, equal number, that's equal frequency. Equal width is how do you sort of design the bins so that each bin, if you have 3 bins, that each bin has the same width and then the same number of items may or may not fall into it, but it has the same width. So maybe buckets of the same, maybe this might have more than this, but if you look at them, that they typically have the same width. That's what we're focusing on here in this video, is equal width binning. So here I kind of want to talk about, feature engineering, deep dive into encoding and binning techniques. So basically, when we're using like machine learning models, for instance, we can do feature engineering, where we can do feature encoding, going from categorical to continuous encoding as well. Like one-hot encoding is very popular for neural networks as well. But pretty much in that kind of encoding, if you have multiple classes, like if you have, classes, like 3 classes, for instance, like in one-hot encoding, what you would do is if you have like classes C1, C2, and C3, then the way that you would encode having class 1 would be 1, 0, 0. For class 2, you would say it's 0, 1, 0, and then class 3 would be 0, 0, 1, for instance. So that would be one hot encoding. So there are multiple different encoding strategies that you can have. And here, what we're going to focus on is like going from continuous data all the way to categorical data through like this feature binning. And we're going to do like equal width binning and then frequency width binning. So equal width binning is also known as uniform binning, and density binning is also known as frequency width binning. So you're sort of, like binning so that you have the same number of objects in each bin. And equal width binning is your binning so that each bin is the same size.
I mentioned both videos that I prepared, but I want to kind of tell you just the key analogies that in each of those videos I'm trying to present. So in equal width binning, basically each bin has the same width. So you can think of it like a ruler. And the analogy is that we have like these four different buckets here. So the rain buckets, and the items are raindrops. So each of them has the same width measured by the ruler, and we are just placing them. And some buckets may get more raindrops than others. The main point is that we just have bins that have the same width, and we're just placing them there. It doesn't matter, they may or may not have the same number of items that fall inside them, may not have the same number of raindrops. But the main focus is just making sure that each bin has the same width. It doesn't matter if they have the same number of items or not. That's what equal density binning instead focuses on. So equal width binning is just focusing on each bin having the same width, and it doesn't matter if they have the same number of items or not. We have buckets of the same width that we're placing out, just maybe cute little different colors. So and then we are displacing them in the rain, and they may or may not have the same number of raindrops that fall. Maybe one is under a tree, and other one is on the table outside if you have it in your backyard, for instance. Wherever you place it, it could, depending on the wind and all of that, like they may not have the same number of drops in them, but we just have the same width buckets. So again, the bin are the rain buckets here, and the items are the raindrops, and the rain buckets have the same width. And equal density binning, instead, the analogy I give is, is about parking garages and, the little cute little cars cartoon. But basically, each bin has the same number of items. Or in odd cases or cases where they're tied, maybe one of the, a couple of the bins may have one or more items than the other. So it really tries to ensure that each bin has the same number of items. It does not matter what the width is. So each of these are sort of focused on their thing. They don't care about the other. Like equal density doesn't care about the bins being the same size, the same width. Sorry, so equal density is what I mean, is it doesn't care about the bins having the same width, having the same width. But equal width binning doesn't care about each bin having the same number of items in it. So equal density is just concerned about each bin having the same number of items. And in cases like if you have like 21 items in 4 bins, you can't have them equally, right? You will try to, if you have 21 items and you have 4 bins, then you would probably have like something like 5, 5, 5, and 6. Like you'll have like 4 buckets. So you have 21 items in 4 buckets, for instance, then you would have like 5 in one, 5 in one, 5 in one, and 6 in the other. That's what you theoretically would get. So that's what I mean. So it's not always exactly the same number of items in each bin, but it really strives for that. Whereas equal width, it's more like precise, because you can always take an interval and divide it into equal width bins. So that's more precise. The analogy that I give here is so the full parking garage that can only hold the same number of cars on each level. So if we think of it like, this cute car here, and this is parking garage, and the bin is basically each parking garage level. So there are multiple levels here, like level 1, 2, 3, and 4. And what I tried to show is that the bin are the levels, and the items are just the number of cars that are parked on those levels. So that's the analogy.
So through those two videos, I try to just cement the ideas, hopefully in your mind, about what these things are, like what is equal width binning with equal density binning, and how they compare. And again, they're just focused on their own criteria. They're not concerned about the others. So equal width is not going to be concerned about each bin having the same number of items inside it, and equal density binning is not going to be concerned about the width of the um, is not going to be concerned about the width of the bins. You know, if maybe this part is a bigger level, but it has more spaced out, or maybe that parking garage is really nice and has like planters and whatnot. So it's like maybe it's possible to have like beautiful bins that are equally that have equal width and equal number of items, but that would be like really beautiful data that we don't often have access to. And these are just two different criteria, and I just want you to have that sense. But I do have dedicated videos for each of these, but I just wanted you to get an overall idea of what to expect in each video. And then equal density binning is like equal frequency binning. So you're trying to make sure, and the garbage bin is trying to say like it's equal density binning. You're trying to make sure that you have roughly the same number of items inside each bin. So each bin has like the same density. That's what's important here. You know, it might be off, give or take, but you know, based on if it's an odd number of things you're putting, I mean, if it's not completely divisible. But here we're trying to figure out, okay, well, we have 12 ages. Our x has these 12 ages. So remember, this is our x here. You know, our x is here. This is our x. You know, a random variable. It's got these values here. We're trying to discretize it into these bins. So yeah, so then this would be, these parts here would be all in like value 1. These would be value 2. And you notice the same number of elements would be in each one. This would be 3. And then this one here would be 4. So roughly, like, you know, they have the same number of items because it works out the 12 divide. 12 is a number of items here. 12 divided by x, you know, now we want 4 bins, number of categories, and this is giant x. X is the, like, this whole random variable of the ages. So this n here is going to be 12 items because there are 12 ages. And x is going to be 4 because we want 4 bins. So the frequency means we want to have 3 items in each bin. That's how this works. So that's like this frequency of 3. That's why we have 3 items here, 3 items, 3 items, 3 items. So based on equal frequency binning, which is also known as equal density binning, the algorithm basically sorts continuous feature values into ascending order, so from like least to greatest, and tries to put an equal number of instances of items into each of the bin, starting with bin 1. So you just start from least to greatest, putting in an equal number of instances in each of the bins. So to figure out how many items go in each bin, you just find out how many total instances or data points you have divided by the number of bins. So for instance, what you'll see here is that if you want 5 bins, it's going to see, like in a normal distribution, what happens is that most of the data is centered in the center. Like most of the density is centered around the middle within 1 or 2 standard deviations of the mean. The results are mostly here. And very little, you can see that this is the density, this dotted line. So most of the data is like concentrated here. So if we have 5 bins, then what happens is that here, for instance, the bins are slightly wider. These bins are wider because they need to have more data points. So they need to have some more data points in them. That's why they're slightly wider. So this is 5 equal frequency bins. Then this is the result if we have 10 bins. So you can see how the bins tend to widen out a bit more because we want the same number of items in each bin, but because there's smaller density on the tails of the distribution, we do need it to be a little bit wider. But this is equal density, so this is 15 bins. So you can sort of see that each bin typically should have the same number of items inside it. There might be one or two differences, you know, because maybe you were trying to divide again like 21 items in like 4 bins, for instance, and then it's not equal. Like one bin might have one more than the other, one might have one less than all the other bins, for instance.
So this is equal frequency binning. So it's more accurately at modeling the heavy populated areas of the continuous features, unlike equal width binning. But because the bins can have very different sizes, like some bins can be really wide and others can be like much smaller, like closer to the middle, there's more density, so you don't need the interval to be as wide to have more items. The key idea is that each bin should roughly have the same number of items in each bin. And because there's lesser objects towards the tails of this distribution, of the normal distribution, the little, I like to think of it like a little bell curve. I'm not really good at drawing that either. You know, there's an empirical rule out there. So because there is less towards the tails are these ending points of the normal distribution. There's more centered here, then the bins that are in the center will be much smaller than those on the edge. So what this is telling us is like, you know, equal width binning again, and credit goes to Satyam Kumar as well for this slide here. And this algorithm for equal width binning is just dividing a continuous variable into several categories having bins or a range of the same width. So this is a way to discretize, to go from continuous data to categorical data. So you have your maximum value and you have your minimum value. And again, this is defined as our range. This part here is the range of the variable. This part here is the range. Min minus max. And x would be like the number of categories. So this x part here is the number of categories that we want here. That's what this x is. That's what this x is. And this little is sort of like kind of telling you how this equal width binning should be done so that you have roughly the same number of items in each. So you have roughly the same width in each bin. So equal width binning is making sure that each bin has the same width. So let's say that this whole thing here from this point to this point is like this whole interval is supposed to be you know, like the min to the max. I want to like kind of divide it up into these chunks that are equal. So this is not exactly equal, but they should all be the same, you know, roughly. But you know, you want them to be equal chunks. So this means that it is inclusive, and so this is sort of like a formula, like min, max on the list, and that's how we do equal width binning. We just figure out, okay, well, roughly what would be the widths, and that's sort of how we define these categories. And I'm going to kind of explain it more. So yeah, this is just another example again about equal width binning when you're given this list of these values for x. Okay, and we want to put them into 4 bins. Okay, so we want to put this value into 4 bins. So we want to discretize these values here into like age bins, for instance. So these are the values sorted from least to greatest. And what we want to do is we want to find these bins. So what we do is we find the maximum value here. The maximum value is going to be, so the maximum value here is going to be at 55. So that's our max value, 55 is our max. And our min value is going to be 10. So if you take 55 minus 10, that's 45. 45 divided by, you know, 12, so 55 minus 10 divided by 4, it's roughly 12. So that's sort of like the formula that's being used here to figure out the width of each bin. And what you want you to observe is that each bin, they have the same width of 12, roughly 12, you know, units. But the number of items in each bin may not be the same. It really depends. So here, there's 4 items in this highest bin, and then 2 in this, you know, third bin. Like 1 here in the second bin, and I think 1, 2, 3, 4, 5, 5 in this bin 1. So that's equal width binning, that, you know, each bin has the same width, but may not have the same number of items inside it. And one of the popular ones is actually histograms try to represent equal width binning. And then for equal width binning, on the other hand, and again, I have those videos that you guys can see for more insights, it splits the range of the feature values into B bins that each have the same size. So it usually works well. So each of these bins is going to have the same size in them. So just like a little ruler. So you take the range. The range is the minimum value. It's a maximum. So range is basically, what range is it is max
minus the min. You take the highest point value, like you look here, the highest value minus the smallest value, and then that's the range, and then you just divide it by b, the number of bins that you want. It usually works well, but what happens is that because each bin has the same width, what you're doing here is you're saying from here to here, that's the same width, from here to here, the same width, from here to here. It's like a histogram essentially, where each of them has the same like width here, width here, width here, width here, width here, width here, like the same ruler measurement. But because, as I was showing, there's less density, there's less data. Actually, what has been shown in the bell curve, so let me show you, is that based on this bell curve, we have, if we look at this bell curve, then if we look at the data in the bell curve here, this is the mean, and we're looking at standard deviations. Then if we look like one standard deviation away, we have 68% of our data there. And then if we look at two standard deviations away, we have around, so this is two standard deviations away. And don't worry if you don't understand these concepts. I will have other videos on this, but 95% of the data is within two standard deviations away of the mean. So the key idea here is that basically most of the data is concentrated around here in the middle. So if you're looking at a normal distribution, you may have some bins. You may have some bins that are instead like very empty, like out here, because you all are having them equal width. So, and there's even less. There's even less data points here and the edges here, so they don't even have many data points inside them. So you may have some near empty bins like towards the end because you're using the same width. So unlike equal density binning or equal frequency binning, which is also what it's called, for equal width binning, each bin has the same width. So you've taken the max minus the minimum and divided it. So you're not concerned about basically the number of items in each bin. You're mainly concerned about the width of the items. So that's sort of what equal width binning is doing. And this is a normal bell-shaped curve, and that's what happens if the data looks something like this, where most of it is within a couple of standard deviations of the mean, within two standard deviations, has 95% of the data. So this is just some concepts for equal width and equal density binning. So yes, there are trade-offs basically. There are trade-offs to each of the different types of binning, to equal density binning and equal width binning, but I suggest trying them out, seeing what you get better results for in your analysis. But do bear in mind the concepts, and I do again have these videos for each of these where I go into depth with the concepts for them. But I want to just kind of highlight this example for equal frequency or density binning and equal width binning. So basically, let's say that you have this data here. You have this data on values 0, 4, 12, 16, 16, 18, 24, 26, 28. You have all this data. You can put it on a number line as well. You can just plot this data. So basically what we can see here is if we just plot these data points. So we have these 9 data points, and our goal here is to place them in 3 bins. And I want to show you how each of these bins binning strategies works, and there are trade-offs for them, which you might have to consider. But this is just a number of data points that are in this over here. And so yeah, this is the number of data points, and then this is the data point value. So we see 0, there's one data point for 0, there's one data point for 4, there's one data point for 12, there are 2, so the count is 2 for 16, there's 1 for 18, there is 1 for 24, there's 1 for 26, and then there's 1 for 28. And we want to place this into 3 bins. So Equal width, what equal width is going to do is it's going to say, let me take my handy dandy ruler. Let's look at and so you sort these data points from least to greatest, and then you look at the maximum value, which is 28, subtract the minimum value, that's 0, max minus min, which is 28 minus 0, and that will give you 28. And you say that you want 3 bins. So you do the 28 divided by 3, which is roughly like 9.333. Each bin should be roughly 9 units wide, like 9.33. So what you're going to do then is for equal width binning, the first bin will sort of be going up to like 0 all the way to like 9.333 is like the first bin here. And then the next bin is going to be going 9.33 plus 9.33, which is 18.66, which is something over here. So that's what you will say for equal width binning. But the first bin is only going to be going for values that are less than 9.33. So each is essentially, the bin should be like 9. So 28 over 3, which is around 9.33 units wide. And we see 0 to 4 is going to be the first bin, because that is, the first bin is here. And sorry, it's not that straight right now, but this is 0 to 4 for the first bin. Then the second bin is like 9-ish to 18-ish, 18.66. So all these values here will be falling in bin 2. And then the last bin is just everything to the end. So that will be like 24 and 26 and 28 will fall into those categories here. So that's how you can view equal width binning. That each bin is at the ruler has the same width essentially. And for equal frequency binning, on the other hand, so again, for equal width, you look at the range, number of bins, and that kind of tells you how many units you have. And you always want the data to be sorted from least to greatest. So for equal frequency or equal density binning, again, it's going to be sorted, but instead you're going to say, hey, I have 9 data points. I have 3 bins, so each bin should have 3 data points inside it. 9 divided by 3 is 3. So this operation is just 9 divided by 3. So that's the operation here. So what you're going to do is you're going to start from the smallest, and you're just going to keep on going in threes. So and that's where it sort of comes into which binning, which equal density algorithm do you use, like because maybe if you're trying to have 10 items into 3 bins, one bin might end up having 4 items. If you have 10 items in 3 bins, you might have 4, 3, and 3, and you just need to determine which one do you put the one that has most in it. So or you could do it another way where maybe all of them have like, or it could land up one way where everybody has hypothetically 4 and 4 items and one has 3, but that doesn't add up to like that doesn't add up right now. But let's say you had like 11 items and you're trying to put them in 3 bins, you could instead have 4, 4, and 3. So then you'd have to figure out that way. But in general, so that determines like how you want to implement this algorithm. And as long as you're basically trying, the main idea is that you're just trying to ensure that the bins by and large have the same number of items in them. And here it works out neatly that each bin has 3 data points. And in this situation, for equal width, each bin is about 9.33 units wide. But for equal frequency or equal density binning, and the density like the bell curve density, like each bin has 3 data points. So we go in order and we take the first 3 here, 0, 4, and 12 on the first bin. Bin 1, then the next 3 come into the next bin here, and then lastly this one comes into the last bin, has 24, 26, and 28. So both kind of really need you to have it sorted, or to at least have it from max minus minimum, and then especially for equal density, because you're just sort of going through and you're just like cars parking in a parking garage level. It's like all the cars are going in till capacity, and you just want that to be filled. You want the parking garage to be filled. So level by level by level. So similarly, bin 1 is taken care of first, then bin 2, then bin 3 here. So for equal width, again, this is sort of how it looks with 0 and 4 in bin 1. So again, guys, the bin 1 is bin 1. Then bin 2 is going to be this one here. and then bin 3 is this. So you can see the contrast and how the bins are with this histogram here. Not histogram, but with this bar chart comparison. So this is bin 0, bin 1, sorry, would equal width binning. This is bin 2, you can see this here. And this one has 4 items again because it doesn't matter how many items are in each bin. What matters is the width of the bin, the ruler being the same. And bin 3 is, again, this should be like 9.33 units wide. And basically the idea is that bin 3 has 3 items, bin 2 ended up having 4 items because 1 plus 2, which is 3 plus 1 is 4. These 4 items here. So again, you have to count this part here. And bin 1 had just 2 items inside it, 0 and 4. So 2, 4, and 3. But for equal frequency, you can see that each of them has 3, so it doesn't matter how wide the intervals are. So for equal width binning, again, like the cutoffs are like 9.33 and 18.66, like, you know, that's where the width of the bins are. And it doesn't matter how many data points are falling in. You set bins with these intervals from 0 to 9.33, and then from 9.33 to 18.66, and then 18.66 all the way up to 28. That's sort of like what you had set in the width. So it didn't matter how many points are in each bin. But for equal frequency, what matters is the number of points in each bin. So you can see, even though the width, the intervals are wider, like this interval is from 0 to 12 here, 12 units here, and then this is just 2 units, 16, 16, 18, just 2 units, and this one is also just 4 units. So you can just see the contrast in how these bins appear based on the binning strategy that you use.
Thank you for watching this. Little Yangshi also says thank you too. Dang, yeah, he's stretched out. But please subscribe to my channel for more updates, and please let me know if you have any questions at all. And again, please do check out those 2 videos I prepared with more detailed explanations on each of these concepts. And they're right in my on my channel under my videos. Thank you guys. All the best.